It is commonly recognized that the adoption of a uniform plumbing code throughout the country would be desirable from the point of view of the plumbing industry, the government, municipalities, and the public in general. The Housing and Home Finance Agency, in the interest of encouraging such a development, sponsored the Uniform Plumbing Code and the formation of a committee composed of representatives of management and labor associations and government agencies interested in plumbing. This committee found it necessary to conduct applied research covering some of the more controversial problems in plumbing. This research was confined to the problems of venting. You will see some of the more important results of the tests as they were made.
Gentlemen, as you will remember, some months ago, the Housing Agency sponsored the formation of our committee. This was for the purpose of securing possible uniformity in plumbing requirements through recommended standards. Standards acceptable to code writing authorities. Because of the lack of technical data and the great number of conflicting requirements in plumbing codes, it was decided to ask the National Bureau of Standards to make a series of tests. Tests of some of the more controversial issues. These included self-siphonage of fixture traps, stack venting, and wet venting, the results of which we'll now see. But let's first hear about it from one of the Bureau's technicians, Mr. Eaton.
Yes, indeed. Well, when the Housing Agency and the committee gave us the go-ahead signal, we started by examining the drawings and the data you submitted. From them, working plans were developed. 3 complete systems for testing were built. One for investigating self-siphonage. The other, another to determine the merits of stack venting. And the third, to study the problems of wet venting. All 3 systems constructed with clear plastic pipe and fittings. All equivalent in dimensions and form to standard materials commonly used. All 3 connecting into an 8-inch public sewer, so arranged that it could be flooded to capacity or reduced in flow. We come first to fixture self-siphonage. As we all know, under certain conditions, when a fixture is discharged, its trap seal is sometimes lost. This is called self-siphonage. Code writers have attacked this problem by limiting the length of unvented fixture wastes. These code requirements vary all over the country, some allowing a length of unvented waste of as much as 10 feet, others limiting this length to 18 inches or even less. Our test showed, as was expected, that the lavatory was more subject to self-siphonage than any other fixture. However, preliminary tests indicated that the discharge of the other fixtures on the stack slightly influenced lavatory self-siphonage. Therefore, it was decided to discharge simultaneously the sink, tray, and water closet with the lavatory. Here, we used a standard-sized lavatory, 20 by 24 inches. But we also used a smaller one, an 18 by 20. On both of them, an 1.25 inch trap was used. With it, test results on each of these laboratories were identical. In each case, the lavatory was filled to the overflow. Then the stopper pulled. This provided a more severe test condition than just partially filling the lavatory. First, we used a standard 1 3/8 lavatory PO plug. Gave us a rate of discharge of about 11 gallons a minute. With this plug, we used an unusually long, unvented lavatory waste. It was connected to a sanitary tee. And here was the result. An 1.25 inch trap seal reduction. Of course, many lavatories are fitted with smaller plugs, the 1 1/8 inch. Using it cuts down the rate of flow to 7.5 gallons a minute. Remember, this is with the smaller plug, the 1 1/8 inch. 0 trap seal reduction. And so, knowing that trap seal reductions will be greater with the inch and 3/8 plug than with the inch and 1/8, the larger plug was used. As you know, venting systems are ordinarily designed to prevent air pressure of over 1 inch of water being formed in these fixture wastes. This means that a half-inch seal remaining in the trap after self-siphonage would be adequate to resist any pressure normally found in the system. On this basis, the trap seal reduction of 1 1/4 inches would be safe. Safe, since 3/4 of an inch of seal remain in the trap. Of course, we know traps and wastes become corroded, fouled in service. This can cause increased self-siphonage. The rate of corrosion and fouling in surface is highly variable. For this reason, we must introduce a safety factor. This consisted of decreasing the amount of trap seal reduction considered satisfactory from 1 1/2 inches to 1 inch. Insofar as vacuums are concerned, a remaining seal of 1 inch in a trap of 2-inch depth of seal offers as much resistance as a full seal. Therefore, on all tests, a trap seal loss of less than 1 inch was considered safe. A trap seal loss of more than 1 inch was classified as unsafe, a failure. Now we reduce the length of the lavatory waste, changing it from 59 inches to 48 inches, keeping the same slope as before, a 1/4 inch per foot. 0 trap seal loss, safe. And so it was concluded that the length of an unvented 1 1/4 inch lavatory waste on a 1/4 inch slope with a short pattern fitting should not exceed 4 feet. But installations vary. The fixture may be roughed in at a slope greater than a 1/4 inch per foot. So we repeated the test you've just seen, using a 1/2 inch slope, keeping everything else the same. In this case, the results were different. Trap seal failure. Therefore, we shortened the length of lavatory waste down to 36 inches, keeping everything else constant. And here again, a trap seal failure. So we reduced the waste length still more, now to 24 inches. All other conditions remaining as before. And this time, only 5/8 of an inch loss. Repeating the test with a metal trap gave us 0 trap loss. And now, from the results of these tests and many others not shown on both metal and plastic wastes, we were able to conclude that the length of an unvented 1 1/4 inch waste on a 1/2 inch slope should be limited to 30 inches. The tests we have just seen have been with the sanitary T-fitting connecting the lavatory waste to the continuous waste and vent. We then changed to a long-turn TY. This fitting is also used frequently, and in some cities it's required, from a safe trap seal with the sanitary fitting to a failure with the TY. So you see, the permissible length of unvented lavatory waste should be less for the long-turn TY than with the sanitary T. But how much less? We again reduce the length, keeping everything else the same. Still an unsafe trap seal. And now a further reduction in length, down to 15 inches. And this time, 0 trap seal loss. Naturally, as before, we rechecked our results, repeating the test with metal, giving us data for a complete, thorough analysis, indicating the length of an unvented 1 1/4 inch lavatory waste on a 1/4 inch slope with a TY should be limited to a maximum of 18 inches. And as was the case with the sanitary T, increasing the slope to a 1/2 inch produced a greater trap seal reduction. Yes, it's an unsafe trap seal, even though the vent is only 18 inches from the trap. Our final reduction to 9 inches. And here, there is 0 trap loss. From these tests, it was concluded that the length of the unvented 1¼ inch waste on a half-inch slope with a long-turn TY should not exceed 12 inches. Our conclusions were based not only on what you have seen here, but actually on thousands of tests. What we've shown you in general has been the maximum obtained in 10 consecutive tests under identical conditions. These tests you have just seen, together with many others, indicate that a large number of variables enter into the problem of lavatory self-siphonage. These include the size and shape of the lavatory, the variation in outlet orifice, the diameter, slope, and length of lavatory waste, the actual dimensions of the trap, and the type of waste and vent fitting on the lavatory drain. As we finished these tests, we had visitors. Mr. Raymond Foley, administrator, and Mr. L.G. Hager, technical director, Housing and Home Finance Agency, and Dr. E.U. Condon, director of the National Bureau of Standards. They have come just in time to see our tests on stack venting. As you know, many codes permit this type of venting. Some don't. So we've been asked to test the merits of this method. All fixtures stack vented, as we see here. A 3-inch soil stack connected to a 3-inch building drain. As you know, in stack venting, there's a tendency for the discharge of the fixtures above the level of the water closet and tub to create a vacuum in the stack. Sufficient vacuum under certain conditions to pull water out of the water closet and tub traps, such as is happening here. But this is a somewhat abnormal installation. The tailpiece of the combination fixture is extra long, much longer than is commonly used, giving us a very low roughing in dimension. Then, too, the sink trap and waste are of smooth material. Now let's see what happens when we use a metal trap and drain on the combination fixture. The tailpiece, though shortened, is still long. The trap, 1½ inch tubing, the one of the many tested which gave the most trap seal reduction. Yet we obtain a safe trap seal in the bathtub and water closet. Here, the test loading consisted of the simultaneous discharge of the sink compartment and lavatory. Our test showed this to be more severe than the discharge of the lavatory and tray. The addition of either water closet or tub to the loading had no appreciable effect. Therefore, the simultaneous discharge of the sink and lavatory constituted a reasonably severe loading. These tests were made with a sanitary T, as this fitting is used most often. However, some cities require the long-turn TY or combination Y and 1/8 bend. So additional tests were made with this fitting. We knew the most severe condition was with the extra long tailpiece. The sink roughed in very low. Hence, we made the tests under the same conditions, pulled the basket strainer completely out, just as we had done before. This substantially increased the rate of discharge over normal use, thus causing the trap seal reduction seen here to be greater than in practice. Gave us an increased safety factor, one to be considered as we look at the water closet trap again. A safe trap seal. More than 50 gallons of water per minute flowing from the sink and lavatory, but the trap seal is intact. To us, this means that for this installation, a long-turn TY is satisfactory for stack venting. But it's not a must. And the same is true with a double sanitary T or sanitary cross. Here we're using it to connect the combination fixture and lavatory at the same level on the stack. The result? A safe trap seal. So you see, stack venting can be considered perfectly safe with any of these fittings. Safe with the double sanitary T or sanitary cross. Safe when a long-turn TY is used. And safe with separate sanitary Ts. Of course, with time, caking and fouling will reduce pipe diameter, increase its roughness, reduce flow rate, all of which will tend to prevent loss of the trap seals. This means fouling and corrosion will provide an additional safety factor for trap seals, at least as far as stack venting is concerned. Therefore, stack venting properly installed on a one-story or the top story of a residence is perfectly satisfactory. Of course, there are other ways of venting plumbing fixtures. Back venting has been used for years. It's perfectly satisfactory. And there's another method. It's used fairly often, too. That's wet venting. And as you know, it's been argued that a waste pipe from one fixture cannot safely be used as a vent for another fixture. So we've been asked to test this type of installation, both for the two bathrooms back-to-back arrangement as well as the single bath and kitchen back-to-back arrangement. But suppose we let Ed Monteith tell you about these tests.
Be glad to. We tackled the two-story first. Here we had two kitchens with two combination fixtures back-to-back on the first floor. On the top floor, we had two bathrooms back-to-back. Here, our problem was to find out if the discharge of the fixtures attached to the wet vent adversely affected the bathtub trap seals. You see, we had a total of 22 fixture units, all of them draining into a 3-inch soil stack. By preliminary tests, we found that discharging both lavatories and bathtubs, all 4 fixtures simultaneously, provided the most severe loading. The additional discharge of the water closet had no appreciable effect on the trap seal of the bathtub. But here, continuous flow through the lavatories was even more severe than filling and emptying them. In the same way, filling the tubs to unequal depths produced a greater load than filling them equally. Of course, we used a sanitary T as well as the long-turn TY to connect the lavatory drain to the wet vent. But we found no practical difference in the trap seal reduction by using either fitting. So, all the tests you're going to see are with the sanitary T. The same holds true for the size of the wet vent. No practical difference in trap seal reduction between the 1.5 inch and the 2 inch. So, we choose the 2-inch wet vent. We started with a long tub waste. But here, with a 1/4 inch drain slope, it's perfectly safe. Then we made a change, increased the slope to a 1/2 inch, had the same fixture discharge as before. And here's the result: failure of the trap seal. So we shortened the tub drain, kept the slope constant, and this is what we found: a safe trap seal. Therefore, a wet vented tub drain of as much as 6 feet on a 1/2 or 1/4 inch slope is satisfactory. We shortened the tub drain still more again having the same fixture discharge. A safe trap seal, but not zero. We kept on shortening the drain length. Now, no loss at all. Therefore, it can be concluded that a wet-vented 1.5-inch tub drain of 6 feet or less is a safe installation. In each test, the trap seal losses were no greater with iron piping than with plastic tubing. Speaking of lengths, during these tests, the horizontal branch between the junction of the tub waist and stack was kept constant at 2 feet, just like the usual installations. But we thought of the unusual case, installation where this distance might be greater. We changed the branch length to 6 feet, repeated the experiments. The results were identical with those on the short length. Therefore, it can be concluded that for duplex wet venting, 6-foot lengths of tub waste are perfectly safe. Safe whether using an 1.5-inch or 2-inch wet vent. But for increased safety, the minimum diameter of the wet vent should be limited to 2 inches.
And now show you the tests on the one-story wet-vented bathroom and kitchen, back to back. These tests were made with a combination fixture and lavatory connected to the wet vent. This represented the usual number of fixtures connected to the wet vent in a single dwelling. Naturally, we made a variety of tests, using different loadings. We found, as expected, the discharge of the combination fixture and lavatory naturally gave us the most severe loading, one which would rarely occur in ordinary use, if at all. But this gave us a large safety factor. On our first try, we used an unusually long, unvented tub drain. The result? 0 trap seal loss. And so we wanted to see what effect a greater slope would have on this installation. We changed it, made it 1/2 inch per foot, kept the drain length at 6 feet. And here's what we found. A slight increase in trap seal loss, but still safe. Then we did some more rearranging. From the 2-inch wet vent we'd been using, we changed to the 1.5 inch. We kept the bathtub drain length constant at 6 feet. But here, the combination fixture and lavatory loading was too heavy. The trap seal reduction, not safe. Therefore, the size of the wet vent should be not less than 2 inches. All results showed the plastic tests were more severe than those with metal pipe. But at present, there are no precise data on the effects of fouling on wet venting. So the Uniform Plumbing Code Committee felt it desirable to apply safety factors to allow for this. First, the test loadings adopted were unusually severe, much greater than ordinarily found in practice. Second, the committee also agreed to limit the length of a wet-vented tub drain to less than 6 feet. Even though, as we have seen, the tests indicate that greater lengths were safe. However, for uniformity, these lengths found satisfactory in the self-siphonage tests will be applied also to wet venting. And so we conclude wet venting of bathtub traps under certain conditions, as you have seen, is perfectly safe. Well, that's part of our story. There's still a great deal to be done.
Many thanks, Mr. Eaton. You know, I've been in the plumbing business over 40 years. These tests are a revelation of what happens inside plumbing systems. Gives us information we can apply in new construction and remodeling in the plumbing industry.
The tests you have just seen have formed the basis for part of the sections in the code covering drainage and venting prepared by the Uniform Plumbing Code Committee. In the opinion of the committee, the tests presented offer a common ground on which code writing authorities may unite in securing uniformity of plumbing requirements for the problems investigated. The adoption of a uniform plumbing code throughout the nation will aid the housing and plumbing industries, it will aid the public at large, and it will aid the continuing effort to adequately house America.